All right, so this is me working Chapter 7 inverted lecture for all of you. I mentioned that I gave everyone credit for giving it an honest attempt, but there are some issues within the answers that I saw that I want to address here to everyone. So if we look at problem number 1, it says provide an explanation for the following observations. Your explanation must include mechanistic considerations. That is, draw the mechanisms. Most of you did that, which was good. And what we can see is that we have two different molecules here. Here we have a secondary alcohol, and here we have a primary alkyl bromide, both undergoing an elimination reaction to give an alkene. However, we clearly see that there's something going on here, going from a 4-membered ring to a 5-membered ring, so we have a ring expansion. And here, the mechanism is such that we don't undergo a ring expansion, and we just get the alkene. And so we need to explain that. And upon looking at this, we need to recognize that the mechanisms of these two reactions is going to be different, and that's what is resulting in the different products that we see. So if we look at the top problem, and again, you all need to draw these molecules out as you do your reactions. One of the things I'm seeing a lot of people doing is using the structures that I've provided and trying to do mechanisms on those. It's very difficult. You need to redraw all the structures. And so we have a secondary alcohol, we have sulfuric acid, and again we need to think of sulfuric acid as H plus and HSO4 minus, and we need to draw that out. It is actually wrong to show the electrons going from the alcohol just as sulfuric acid without showing anything else. You have to show how this is actually flowing, and so the electron pair from oxygen on the alcohol gets protonated. We end up forming the protonated alcohol. This is a secondary alcohol, so I know that the water can leave, and so we're going to break that carbon-oxygen bond like that. And this, of course, is a reversible reaction as well. I end up with a secondary carbocation and water. And now the cardinal rule of carbocations needs to come into play here. I know that secondary carbocations can rearrange to more stable carbocations. And so what I can see here is if I number my carbons, 1, 2, 3, 4, 5, and 6. Okay. I could have a hydride shift. So there's a hydrogen on carbon number 3 that could shift to carbon number 2. Resulting in a tertiary carbocation on carbon number 3. That's not going to happen here, even though tertiary we say typically is more stable than secondary, but it's not in this case because our cyclobutane ring has 90-degree bond angles, so that would actually be less stable than the secondary. But what can happen is we can also have a alkyl group shift by shifting, and I'm going to use the carbon 3 carbon 4 bond. You could have just as easily used the carbon 3 carbon 6 bond because it's symmetrical. But I'm going to show this shift. So the bond between, or the electrons in the bond between carbon 3 and 4 are going to shift over and make a bond between carbon number 2 and carbon number 4. So this is a rearrangement. That ring expands to 5 carbons, and so there's carbon number 1, there's carbon number 2, there's carbon number 4, there's carbon number 3, 6, and 5. And now the carbocation is on carbon number 3. It too is a secondary carbocation, but it's more stable because you have the loss of ring strain in the 4-membered ring. Now we can have a hydride shift to give the tertiary carbocation that is much more stable. So I'm just going to draw on that hydrogen so you all can see it. So again, 1, 2, 3, 4, 5, and 6. And now what happens is water comes in, which is still there, and it functions as a base. And I'm just going to have it remove the hydrogen there. And that's a bad arrow that hard to see because of the numbering, I'm sorry about that, or to the carbocation, and that's how we end up with the product that we get. Okay. Now if we look at the second problem, what I recognize is that I have a primary alkyl halide, and so I can't generate a carbocation. So the only thing that can happen here is dBu is going to function as the base, and I'm just going to abbreviate it as B. And so we end up getting a beta elimination, and we end up with the product in that one step. So that's a double-headed arrow. Let me draw that a little more clearly for you all. So the reason that we get two different products here is because the first one is going through an E1 elimination, whereas the second one is going through an E2 elimination. And E1s allow for go through carbocation intermediate, which allows for that rearrangement to occur. So that should have been in your, what I'm saying to you should have been somewhere in your explanation as well as these mechanistic considerations. Question 2 said, provide the product and mechanism in the following reaction. So again, very important, redraw your structures. So here we have a secondary alcohol. We have H3PO4, which we can think of as H plus and H2PO4 minus. Okay, it's another one of those acids that we talked about being a dehydrating acid, so it will protonate the alcohol, and of course this is a reversible step. Water leaves. You get a secondary carbocation. That can rearrange. And in this case, we're going to get a methyl shift and end up getting a tertiary carbocation in the process. And now the water comes in and acts as a base. And gives the product. Question number 3 was provide an explanation for the following observations. Your explanation must include mechanistic considerations. So, what we look at here is that it looks like we have kind of the same type of starting material overall, right? The only difference is one is an alcohol, one is an alkyl halide. And we're doing eliminations in both cases. The top example gives us what looks like you should get from a Zaitsev rule kind of situation, but the bottom one seems to have violated Zaitsev's rule, and so we need to explain why that is. So if we look at the top example first, we have this stereochemistry, right, where the alcohol and the methyl group are trans to one another. We're going to react that with sulfuric acid. Again, we can think of that as H plus, HSO4 minus. We're going to protonate that alcohol. So this suggests we're going to go through an E1 elimination. Oops, let me get my structure there. The water leaves. We end up with a secondary carbocation, which can rearrange to the tertiary, because remember there's also a hydrogen here that's not drawn in, right, on that particular carbon, and so we can get the hydrogen to actually shift over to the secondary carbocation, and in doing so it generates a tertiary carbocation, which is more stable. And now the water can come in and remove one of the beta hydrogens. I'm just going to draw that one. And you end up with the product that we see. Follow Zaitsev's rule. The second problem, a little different. So here we have a situation where we have an alkyl bromide. Bromide course, or bromine is a pretty good leaving group. But we're using sodium ethoxide, and of course ethanol is the solvent. And so all of this seems to suggest that we've got some other type of mechanism going on here. So it doesn't look like we're going to generate a carbocation. And so whereas the top one went through an E1 elimination, it's looking like this one's going to go through an E2 elimination. And in order to understand this, we need to build a model. So here's our six-membered ring. Okay, and I know that if I turn it like this, I know that coming towards us is the methyl group. So I'm going to put the methyl group on here. Right? So if I flatten that out, that would have the methyl group coming towards us. And I know on this carbon the bromine's going away from us. So I'm going to put that right there. There we go. Right, so there's that particular, you can see that the methyl group and the bromine are trans to one another. And so if we look at this, right, there's no hydrogen on this carbon that is anti-periplanar to this leaving group. Remember that we have to have the hydrogen and the leaving group have to be anti-periplanar to one another, or trans if you will. Well, if I look down this carbon-carbon bond, you can see that the hydrogen and the bromine are actually syn to one another. So this can't undergo an elimination. The base can't come here and abstract this proton, and these electrons get behind here to kick out the leaving group. But what I do notice is that the hydrogens on this carbon, this hydrogen is anti-periplanar to this bromine. And so what can happen now is the base can come in and abstract this hydrogen and form the double bond and have the leaving group leave. And so in doing so, that's why we end up with the product that we get here. The hydrogen on this particular carbon atom is not anti-periplanar to the leaving group, and so we don't see that formation. And so it appears that this is a violating Zaitsev's rule, but it's not. It all has to do with the fact that an E2 mechanism requires the beta hydrogen to be anti-periplanar with the leaving group. Okay, and that's why. All right, let's look at question number 4. It says, provide an explanation for the following observations. Your explanation must include mechanistic considerations. Draw the mechanism. Well, what I can see is I've got a secondary alkyl bromide, and I'm going to mix this with silver nitrate. So that's an ionic compound, as you'll recall from general chemistry. It's an ethanol as solvent, a polar protic solvent. Polar protic solvents can dissolve both the alkyl halide, because it's an organic solvent and an organic molecule, but it can also dissolve the salt, and that's kind of important. Now, one of the things that you need to remember, think back to your general chemistry about your spot tests that you did in lab, right? What do we know about silver ions? Silver ions will precipitate with chloride or bromide or iodide, or that is the halogen atoms. They're insoluble in things like water, and you precipitated those out. The same thing happens here. Silver serves as a way to remove the bromide under mild conditions. And so what happens is the carbon-bromine bond, those electrons will go to the silver to form silver bromide, which precipitates out of solution. And then you generate the secondary carbocation plus plus the nitrate. And it turns out that nitrate is not a good nucleophile because of all the resonance structures. And so I end up with a secondary carbocation that will rearrange to a more stable tertiary by a methyl shift. So the one that I've got bolded there is the one that shifted. I now notice that I have a hydrogen on this carbon atom, and so you could have your conjugate base come in and abstract and form the alkene. And of course that's like nitric acid being an ethanol, which would be the same thing as ethanol being protonated with nitrate. So you can use either the ethanol or the nitrate as the conjugate base. I don't really care in that particular context, but that's how you end up with this alkene. And so the important thing here was to recognize your general chemistry rules for the solubility of silver halides. That's what was helping form the carbocation in this case. And it turns out that things like silver nitrate or other silver salts, are useful in promoting this type of chemistry with alkyl halides. So with like secondary, tertiary alkyl halides, you can get carbocations under very mild conditions by exposing them to a little bit of silver. Okay, question 5 was to provide an explanation of Zaitsev's rule. You must provide an example reaction in your explanation. I'm not going to go over this one here on the YouTube. Look this back up in the book. It gives a very good explanation, and you can go and just read that there. So hope this helped explain some things. I think you all are getting better in your explanations, but there were still a few things that you needed to be a little more explicit about. So keep up the good work, and I'll see you all next week.